Hi, welcome to this video. In this video I'm going to explain how direct memory access works on a PIC microcontroller and how you can use it with the YAL programming language. So what will be the contents of this video? First, a short introduction. Then what DMA direct memory access is and how you can use it. Then I will show two software solutions, one solution without the DMA and one with DMA. I will show the setup and then show a demonstration video, and I will do a speed comparison between the two solutions, so the one solution without DMA and the other solution with DMA. And at the end of this video you can find some references. So if you want to transfer a lot of data fast, some PICs have a direct memory access that you can use. And in this video I will explain how DMA works and how you can use it with the YAL programming language if you want to transfer a lot of data. What I'm going to do in this demonstration, I will copy a YAL logo to an LCD which is connected via the SPI interface. And in the first solution I will do it, let's say, the standard, the traditional way, using a CPU. And the second solution I will show this demonstration using the DMA. And then I will do a comparison in the speed between the two solutions. So, direct memory access, what is it? If you have a PIC with a direct memory access hardware on board, you can send data between peripherals of the PIC without the CPU intervention. So this makes data transfer faster, and the CPU can spend time on other tasks. So it doesn't have to wait for register flags, or it doesn't have to handle the interrupts. And especially if you have to transfer a large amount of data, it will save CPU time and also transfer time. And the data can be obtained from various PIC sources and can be sent to the various PIC peripherals. But not all PICs have the DMA hardware on board. So for the 8-bit PIC microcontrollers you can find them in the PIC 18F family. So if you look at the DMA setup, it looks as follows. So you have one or more DMA controllers, and then DMA transfer is started by a trigger. But before using it you have to set, of course, the control registers. You have to set a start address where you can find the data, the source size, so the size of the data that you want to transfer. Then a destination address where you send the data to, and the destination size. So PIC controllers have multiple independent DMA channels that you can use. And the data is transferred from a source address to a destination address, but without the use of the CPU. And sources can be PIC peripherals, registers, it can also be RAM or flash. Destination address are the PIC peripherals or the RAM. And there's a system arbiter that you can use to change the priority of each DMA channel. So for the software solution, I'm copying a YAL logo of 100 by 100 pixels, which is stored as a constant word array in the flash. And the contents of this array is copied to the LCD using the SPI interface. The LCD uses one word for one pixel, but since we're using an 8-bit microcontroller, we transfer that as 2 bytes. And in the first setup I'm using the CPU. We just copy the contents of this array using a for loop, and that looks as follows. So we have the image size and we use an index. Then we copy one word from this array to a data word. We send the data word as a high and a low byte to the SPI interface, and that's it. The image size is 100 by 100 words. That means 10,000 words, or in bytes it's 20,000 bytes. And in this case the data is written with high byte first, which is called big endian, but normally YAL itself uses little endian. So the second solution is a DMA solution. So what we need to do, we need to program the DMA registers as follows. So we first select which DMA to be used, so this is the first one. we select the flash as the source because our constant array is in flash, and we also indicate that we want to increment the pointer of this flash array, because each time we transfer a byte we want to transfer the next byte. Then we define the source size, which I have defined as a constant, the DMA transfer size. Then we have to define the start address of this array, and for that we use the whereis command from YAL. Then the destination size is 1 byte because we're transferring to one SPI register. We have to set the destination address, and also we can obtain that from using the whereis command. Then we need to define the trigger, and the trigger to start the source is number hexadecimal 19, which you can find in the data sheet. And then we have to set the arbiter priority for we set the priority 1, the default is 7. And then at the end of this you need to follow the following sequence for the DMA operation. So now we have defined, let's say, what the source is and the destination and the size of the message. We need to transfer this data via DMA. So we need to transfer 20,000 bytes, and we do it in 100 steps, which I call the DMA transfer count, of 200 bytes, which I call the DMA transfer size. So in each DMA transfer we will transfer 200 bytes of data, and we do that 100 times. So this is done as follows. You first enable the DMA, and then we have a for loop. So we do this 100 times. We start a DMA transfer, we wait for the DMA to be completed, then we adjust the source address, so we add 200 bytes to the start address of the source, and this is repeated until all data is transferred. And at the end we disable the DMA. Okay, so what you will see in the video is I'm using a PIC 18F15Q40 microcontroller, which is connected via the SPI interface to the LCD. Both devices operate at 3.3 volts. The PIC runs at a clock frequency of 64 MHz. The LCD can only handle an SPI clock of at most 6.6 MHz, so I have configured the SPI clock to run at 6.4 MHz. In the demo you will see a transmission using the CPU, and after a pause of 5 seconds you see the DMA transfer using the DMA, and this cycle repeats continuously. And when a transmission is active, a red LED will light up very shortly. And the transmission time is also shown on the display and is measured in instruction cycles. And then one instruction cycle is 63 nanoseconds because we're using a 64 MHz clock. Okay, so in the video we have seen the two solutions, and I measured the on time of the LED using an oscilloscope. And for the CPU transfer it takes 73 milliseconds, for the DMA it takes 26 milliseconds. And also you have seen on the screen the instruction cycles it took to do both the transfers. And as you saw from the video, the DMA transfers almost 3 times faster than the CPU transfer, since it uses less instruction cycles. If you want to know more about YAL or the YAL programming language, you can visit the YAL website. If you have questions on how to use YAL, you can visit the YAL list Google group. If you find bugs or you have specific requests, you can visit the YAL lib Google group. And all YAL sources, including the sources for the compiler, can be found on GitHub. And also this software that I'm using for this demo can be found there. I hope you liked this video, and thanks for watching.